Okay, this is a review for exam one. So if you try to discuss about the concept map for chapter one and two, so we started with what thermodynamics is. Thermodynamics is a study of triple E, right? So a study of energy, equilibrium, and entropy. There are so many applications of thermodynamics. One way to study is through the applications. It is used in engines. It is used in uh, Rankine cycle. It is used in refrigeration. It is used in air conditioning. So there are so many applications of thermodynamics. Um, when you do the numerical problems in thermodynamics, you could solve the problem using SI unit, or you could use English unit or US customer unit. In SI unit, the primary variables are mass in kg, length in meter, and time in second, and you get force in Newton. Um, there are many secondary variable as well, like velocity could be in meter per second, specific energy in joule per kg, power in watt. These are some of the important variables. In English unit, the primary variable mass, it is sometimes in slug and sometimes in pound mass, length in feet, time in seconds, and force in pound force. Secondary variable, for example, velocity could be in feet per second. Specific energy could be feet pound force by kg. Sorry, this is not kg. It should be per pound mass or slug. Power in feet pound force per second. Also, you can study thermodynamics through two different approaches. Macroscopic, that's the big picture. That's what this course is focused on. Microscopic is molecular level, which is the statistical technique, which we will not be using here. So macroscopic in you can study thermodynamics through law of thermodynamics. So you have four laws that relates to the thermodynamics, which is general law of thermodynamics, which is the basis for temperature measurement. First law of thermodynamics related with the conservation of energy, and this is the equation you have. Energy in minus energy out is change in energy of the system, and energy in and out relates with the energy transfer through the heat transfer, work transfer, and mass transfer. And change in energy of the system relates with change in energy due to kinetic energy, potential energy, internal energy, and flow work. So that's the conservation of energy. And you can see here the laws of thermodynamics can be written for different types of system. So you have closed system in which there is only transfer of energy due to Q, heat transfer, and work transfer. There is no mass transfer. Whereas in open system you have the energy transfer due to heat transfer, work transfer, and energy due to mass transfer. In an isolated system, there is no any transfer of energy, so you don't have Q transfer or work transfer or the mass transfer. And you can apply this system for different processes, like it could be isobaric process where pressure is constant. It could be isochoric or isometric process where volume is constant. You could also apply for isothermal process where temperature is constant. Adiabatic means there is no heat transfer. Polytropic means defined by PV and equals to constant. So you could see here the energy laws could be applied for different types of system, and also for each one of these systems you can write the energy equation in kilojoule per kg form, or specific energy form you can write in joule or kilojoule form, or total energy form, or also you can write in power form, that is watt or kilowatt form. So this is kind of summary for chapter 1 and chapter 2. Going forward, so you have different type of thermodynamic system, like as you discussed. Open system where you have energy due to mass flow, work transfer, and heat flow. In closed system, you don't have the energy due to mass flow, whereas in isolated system, you don't have any energy transfer at all. And then property, we have so many property. The property could be intensive property or extensive property. Intensive property does not depend on mass, whereas extensive property depends on mass. The property could be like pressure, temperature, uh, volume, specific volume, and it could be density. It could be a specific volume. It could be a specific weight. So you should know how to calculate density. Like density is mass per unit volume. Okay. Specific volume is the reciprocal of the density, and a specific weight is the formula is density multiplied by uh, the acceleration due to gravity. And specific gravity is, if you know, density of water is at 4 degrees centigrade is assumed to be 1000 kg per meter cube. So if the specific gravity is given, you can find density using this formula. Make sure you know what is the density of water at 0 degrees centigrade, which is assumed to be 1000 kg per meter cube. So for instance here, the density of the fluid is given here, 0.5 kilogram per meter cube. You have been asked to find a specific volume. So a specific volume is 1 by density, so 1 by 0.5. So whatever you get, that will be in meter cube per kg. If in this question it asks you to find a specific gravity is density of water at 4 degrees centigrade. So if this density is known, which is 0.5 kilogram per meter cube, and then 1000, so that would give you specific gravity. If the specific weight is asked here, like here, the specific weight is density multiplied by acceleration due to gravity. So density is known here, acceleration due to gravity is 9.8 meter per second squared. So this type of problem could be asked in the exam. So unit system, as I discussed, there are two unit system, SI unit system and English unit system. And in SI unit system, mass is kilogram, length in meter, time in second, and force in Newton. Whereas in English unit system, pound, the mass is in pound mass or slug, length in feet, and time in second, and force in pound force. Like here, so you could be asked to solve the problem using any unit system. So for instance here, find the kinetic energy. So you need to find the kinetic energy, which is half mv square of 10-pound mass object moving at 5 inches per second. My suggestion for this type of problem is to convert everything to the basic unit and do the calculations. You need to find the kinetic energy in feet pound force and then in VTU. So for this one, mass is in pound mass, so convert to slug. So it will be 10 by 32.2, and then velocity is in inch per second, so convert to feet per second. So this is in feet per second and this is in slug. And if you do the calculations, the unit of kinetic energy would be feet pound force. Okay, now in order to convert to BTU, you have to use the conversion table. And if you see the conversion table, 1 BTU is pretty close to, I think you can look at the table, 787.17. So you could write this as 1 BTU divided by 787.17 equals to 1. So, and use this one to convert whatever you get from here. Okay, so you could see here 1 BTU, as I said, is here. This, so this table you can bring it for the exam, so that depending on what unit conversion you want, you can make use of this. Then we move on to the first law of thermodynamics. In the first law of thermodynamics, energy in minus energy out is the change in energy of the system. So energy in here could be due to heat transfer, could be due to work transfer, due to energy due to mass transfer. And so is the case here too. And change in energy of the system is due to change in kinetic energy, due to change in potential energy, and due to change in internal energy, and due to change in flow work. So these are the things which you need to take into consideration. Okay, this is the first of thermodynamics, or conservation of energy. And you should be able to write this equation in different form, like in the form of total energy. If that is the case, it has to be in kilojoule, everything has to be in kilojoule. Energy per unit mass, or in other words, specific energy, everything has to be in terms of energy per unit kg. And sometimes you may have to do in terms of power as well. So everything has to be kilojoule per second. So you should know how to write this equation in different form. Another important thing is this is an important variable which we come across, which is the mass flow rate. And mass flow rate is density, cross-section area of the pipe, and then average velocity. And then this is mass flow rate, m dot, which unit is kg per second. And sometimes we use q, or also v dot, which is volumetric flow rate, which is just this value. Cross-section area multiplied by the average velocity would give you the volumetric flow rate, and the unit is meter cube per second or feet cube per second. That means how much volume of water or any fluid is flowing per unit time. That's what uh, the volumetric flow rate or flow rate is, and this is an important variables in thermodynamics. Okay, so you may be asked to calculate these variables um, in the numerical problem. So as shown here, you can express the energy equation in different form, in kilowatt form, kilojoule form, and kilojoule per kg form. And you can write in extended form as well. So, energy in, energy out, it could be due to heat transfer, it could be due to work transfer, it could be due to uh, energy due to mass transfer, and the right hand side of the equation is change in energy of the system. It could be due to change in kinetic energy, potential energy, internal energy, or the flow work. And again, you can write this equation in all three forms. So that is very important: kilojoule per kg, or kilojoule form like in previous equation, and then also in kilowatt form. And this equation can be written in all three forms for closed system, open system, and isolated system, which you will be learning later on. For instance, here, calculate the total potential energy in BTU of an object with a mass of 200 pounds when it is 10 feet above datum line. So you need to find the potential energy in BTU. So potential energy is mgg, right? Again, convert everything to basic unit. For instance, convert this to slug by dividing 32.2. 10 feet is already in basic unit, and then this one is in 32.2. So your answer would be in feet pound force. Now again, use the unity conversion table to convert this to BTU and get your answer. Okay. So in this problem, you have been asked to find out the mass flow rate of water in a pipe. So you have a pipe which is 10 centimeter in diameter, and moving with the velocity of 2 meter per second, and density is 1000 kg per meter cube. So this is given. You have been asked to find the mass flow rate. So the mass flow rate, so how fast per kg per second, is rho a v average, where this is average velocity. So density is given 1000. Area of always the cross section area. So this cross section area is, since it is a diameter is given, so it is a circular pipe, so pi by 4 d square, and convert this 10 centimeter to meter because we want everything to be in basic unit. So 0.1 whole square, and then V average is already given in SI unit, which is 2 meter per second. So everything is in basic unit, so you can calculate the the mass flow rate. For the volumetric flow rate, it's just simply this one. So volumetric flow rate is the cross-section area multiplied by the average velocity. So cross-section area pi by 4 d square for pi by 4 d square, and then for average velocity, it's 2 meter per second is given. So you can substitute, and your answer should be in meter cube per second. So how much volume per unit time would give you the volumetric flow rate of water. Efficiency, sometimes the efficiency of some of the machine could be asked. Always efficiency is how much your desired output is, and then how much is the input divided by how much is the input. You can find the efficiency for different types of machine, like pump. For pump, the input is electrical input, output is shaft output. Sorry, for motor, the output is shaft output, and then input is electrical input. For generator, so you have the output is how much is the electricity output, and then input is shaft input. So the key thing is always how much output divided by how much was the input would always give you the ratio of the energy would give you the efficiency of that particular engine. So if you have a system, then for a system there is a turbine and generator. Then if you want to find the overall efficiency, then you need to multiply the efficiency of this, multiply efficiency of this. If you have another system as well, you need to multiply the efficiency of this to get the overall efficiency. Okay, now we are coming to the third chapter of our textbook, which is on property, how to find the property, of pure substance. Okay, that's the goal, and we are trying to get this through the property table. And from exam point of view, most of the questions should be from this chapter. Okay, so the first thing is always whenever you read the problem, figure out what type of substance is that. Is it water? Is it some kind of refrigerant, or any other substance? It could be air, it could be any other substance, it could be nitrogen, anything. Okay, so that's the first thing. Just underline what substance it is. Now you should look at the problem and see the value of the variable. Is it given in SI unit system, or is it given in unit system? So you do not mix up two systems. You either do everything in SI unit system, or you do everything in English unit system. If in the problem it says, mass is 10 kg, then it is SI unit system. The volume, specific volume meter cube per kg, it is a SI unit system. So for water, SI unit system are in appendix 1, and English unit system are in appendix 2. Okay, now it is the same thing, for water or refrigerant. I have shown here this concept map for water. How do you find the property? Now we know it is water. Let's say it is water, and it is SI unit system. Now the next thing you need to figure out is whether the water, where does it lie? Whether it is a subcooled water, or it is a saturated water, or it is a superheated water. That's what we need to figure out. Okay, in subcooled state, properties are only dependent on temperature, whereas in saturation, pressure and temperature are dependent. So if you know the pressure, we know the temperature for the saturated case. And then superheated, pressure and temperature are independent. So once we are here, some certain conditions are provided. You need to figure out where does it lie first, and then once you know where it lies, you can find the property based on that. You can see there are three cases. Case one is, in most of the cases, if the pressure and temperature are, this is in general, okay, if pressure and temperature are given, so this is given, pressure and temperature are given, and you need to find where it lies. So if that is the case, so you have to know this pressure, temperature and volume plot, and then pressure and volume plot. This is important. So if pressure and temperature is given, then you can either look at pressure based table. So for the pressure based table, if you see here, you need to look at the table, the saturation temperature at that corresponding pressure. And if you find that that particular temperature, whatever the temperature T is greater than T saturation. See, so for instance, this is temperature and volume plot. So this line for this pressure, this is a T saturation. So in this region, you see here, this temperature is always greater than T saturation. So in this region, so this is a superheated region. So if T is greater than T saturation, then it would be superheated. This in subcooled region, if you see here, T is always less than T saturation. So that would be subcooled. And in this region, in the saturated region, T is always equals to T saturation. So this is the saturation region. The other way is you can also look for a given temperature. You can look at the temperature based table and see how the pressure is. You should always compare with the saturated pressure in this case. So if you see the plot between pressure and a specific volume, for saturated cases, see if you try to look at this one here, so this one is P saturation. So in the superheated region, you see here, P saturation is here, and all these values of pressure are less than P saturation. So P here in superheated region are less than P saturation. Whereas in this region, you see here, P is always greater than P saturation, that is in subcooled region. Whereas in the saturated region, P is always greater than P saturation. So this is the first case. So in the first case, I'm saying that if pressure and temperature are given, you always try to compare with the saturation pressure value and saturation temperature value and figure out where it lies. Once you know where it lies, then go to that particular table and find the value of the property. So there are two steps. First step is to figure out where it lies, and once you figure it out, you need to go to the specific table based on what we find out. For instance, if you find it to be superheated, then you need to go to table A6 for water and then find the property value. If it is subcooled, you have to do it accordingly. If it is saturated, you have two tables. One is a pressure based table F5, and then you have a temperature based table which is A4, and then you can find the property accordingly. Okay, so that's the first case when the pressure and temperature is given. Second case is either pressure or temperature and any other property. It could be a specific internal energy, it could be specific volume, it could be specific enthalpy is given. In that case, again, you are comparing with this subscript F and G. That means you are comparing with these values. These are, it could be UF, HF, it could be UG and HG. So you need to always compare with this value. See, we are always trying to compare with the saturated region value. So if it is superheated, so at a given pressure or temperature, again, you need to look at the saturated table and see if, now it doesn't have to be all these values will be given on either internal specific internal energy or specific volume or enthalpy. If it is given in this region, always these values are greater than UG. This value UG is a case of saturated vapor. So if these are equal, any one of these, whatever is given, is greater than this UG or HG or entropy G, it is a superheated region. That's how you know it. And once you figure out it is in superheated region, the next step is to go to the superheated table and get the value accordingly. So two steps. First is to find where it is. Next is to go to the table and get the value of the property. Now in this subcooled region, you could see in the subcooled region, the value you need to compare with this subscript F, right? So this is the saturated liquid, so you need to compare with the saturated liquid, which is specific volume at F, saturated liquid, HF or SG, SF. So you need to always compare with that. If it is less than these subscript F value for any property, then it is in the subcooled region. And we know in this region it is only function of temperature, and this property there are two options now. You could use subcooled table. This is one option. And the easy option is, since it is only function of temperature, any property is equals to subscript F at that particular temperature. Not just the internal energy, specific energy. You could do the same thing for the enthalpy, you know, for entropy, and so on. So this is a very important consideration. Sometime in the subcooled region, this property may not be available. So in that case, you must have to make use of the saturated table to find the property in the subcooled region. Okay. Now, if this property value at that particular pressure or temperature are equals to um, UF, VF, or HF, depending on what properties are given, then this is a saturated liquid region. If they are equals to VF, VG, UG, then it is a saturated vapor. Okay, and sometimes the value may be in between this UF and UG, or enthalpy value, specific enthalpy value may be HF and HG. So in that case, it is a saturated mixture. So in that case, you must calculate the value of the quality. Without knowing the value of quality, you won't be able to find any property value. Okay, so the if x equals to 0, then you know it is a saturated liquid. It x equals to 1, it's a saturated vapor. So don't think that in a superheated region x equals to 1. There is no x equals to 1. X equals to 1 indicates to the this line. So you don't have any quality. You don't talk about quality either in superheated region or in the subcooled region. The third case is sometimes the value of quality is given. So in that case, if x equals to 0, then you know it's a saturated liquid. If x equals to 1, it's a saturated vapor. And if x lies between 0 and 1, it is a saturated mixture. And by looking in the sum of the problem, if the quality value is given between 1 and 1, 0 to 1, or 0 or 1, then we should know it is a saturated mixture region. So if you know these three cases, you should be able to figure out where the property lies. That's the first step. Second step is, once you figure out where it lies, you have to go to the specific table and then find the property value. So this concept map is very important. I just explained you for water. You could do the same thing for any other substance as well as any unit system. So the one which I have shown here is for SI unit system. If it is English unit system, you have to go to the appendix 2 and follow the same process. So this is kind of guidelines moving forward. Like in this problem, I think we did in the class, for instance, for problem A, just following the same concept map, the pressure is given and then the quality is given. So you know it's a saturated mixture because the quality value is 0.6, right? So you can find the property accordingly. It's a saturated mixture. So if you know P, we know the temperature corresponding to this, because in the saturated mixture, pressure and temperature are dependent. So this is T saturation. Okay, and then once you know X, you can find U, because we know UF, UZ, and then UFZ. In the second case, temperature is given and then the property value is given. So this is the second case. So at that temperature, you need to see in the table what is UF and UZ, and then see whether this is greater than UG, less than UF, or it lies in between. And based on that, you need to figure out where it lies, and once you figure out where it lies, then you can find the value accordingly. In the third case, the pressure is given and then energy value is given. So this is the second case. So at that particular pressure, find how much is UF, how much is UG, and then compare with this one. And depending on that, you can tell whether it lies in the subcooled region or compressed region, or it lies in the saturated region or in superheated region. So this is the case 1 where temperature and pressure is given. So you need to see, you could do either one of these. At temperature, you can look for P saturation and compare with this pressure, or you can look at the pressure table and compare with the T saturation and make your decision where it lies based on the value which you get. In the last one, again, the quality value is given, x equals to 0, which means it is a saturated liquid. So for saturated liquids, so the properties are UF. If it was x equals to 1, then the property would be UZ. So this is how you need to solve the problem based on what is given and what has been asked. So this is exactly the same thing that we discussed before. Um, uh, it's very important how you to know how to do the interpolation. Sometimes the value are not given, and then for instance, like here in this problem, what is the enthalpy of saturated liquid at 72 degrees centigrade? So at 72 degrees centigrade here, the values are not given. It's between 70 and 75. So we don't know the value at 72. So in that case, we have to do interpolation. You'll definitely get a problem in the exam which requires interpolation. So you should know exactly how to do the interpolation. Okay. So for that, you can choose this, any two. Um, so you have any two x1 y1, and then you have x2 y2, and then do we want to find, sometime x is known, so this is xy, sometime x is known and y needs to be found, or sometime y is known, x needs to be found. So this is the 2-point formula that is going to be used in order to find the unknown. Maybe in this problem you have enough to find at 72, because we know the enthalpy at 70 and we know at 75, but we don't know at 72. So in these cases, you need to do the interpolation and find the answer using this 2-point rule. And again, as I said, it's going to be 100% sure you are getting question that requires some kind of interpolation. So make sure you know how to do it. If the value is not given, then you need to carry out the interpolation. Okay, like here. So this is how you do the interpolation. For superheated vapor, beside using the um, table, property table, there are also other ways how by which we can find the properties. So one being using the ideal gas equation. This is the least accurate but the easiest way. And to compensate for some error, we can also use what do you call it, the compressibility chart. Is the medium accurate. Okay, the property table are good, but they are bulky. You need so much of data, and that's kind of bulky. So for superheated vapor or gases, the other option is to make use of ideal gas equation or ideal gas equation with a compressibility chart. For ideal gas equation is just PV. This is a specific volume. Remember, you should know that. And then you should exactly know what should be the unit and what this parameter means. That's where you get wrong. So here P has to be an absolute value. If it is an SI unit, Newton per meter square, the specific volume in meter cube per kg. R is a gas constant. If it is in kilojoule, try to convert to joule per kg per Kelvin. Okay, and then temperature, this is where you tend to get wrong. So it has to be absolute in Kelvin if you are using an SI unit. If you are using in US custom unit, it has to be in Rankine, not in Celsius. So this should not be in Celsius. This pressure and temperature has to be absolute unit. So temperature in Kelvin or Rankine, pressure in Newton per meter square if you are using SI unit. And sometimes the same equation can also be written as PV is equals to MRT. So in this case, this V become um, volume, because specific volume is uh, volume per unit mass. So if you just substitute this one, you get this equation. So sometimes if you want to find the mass. Okay, and this is how the universal gas constant is related to the gas constant. And the values, so the table A1 becomes handy because it gives you the value of molecular mass as well as this one which we'll be using in the equation. CPV is RT. So the gas constant, depending on what gas you are using, you need to look at if it is air, R is this, and remember the unit is in kilojoule per kg per Kelvin, so you need to be careful in changing the unit so that you get the basic answer unit system. Okay. So there are certain errors associated with the ideal gas equations. So to compensate for that, we calculate what we call as a compressibility factor. So instead of PV, um, RT, you have now PB big G RT. So if this equals to 1, then that means um, it is ideal gas. As it goes away from 1, then uh, it doesn't become like ideal gas. Okay. So the question is how you can calculate the value of Z, and for that you have to make use of the chart. So for that we use this chart in which you have reduced pressure on the x-axis and then the value of G on the y-axis, and these are the value of reduced temperature. See, this is how the reduced temperature defined, and these critical values of pressure and temperature are found from table A1. This is the chart which I showed to you, but you could use this chart from the textbook. See, it is the same chart. It is here. It is given up to 1. So here up to here is shown here, and then this is like up to 7. So this is PR, and these line are uh, for TR, and this dotted line. Okay, that was not shown before. These are for BR. I think there was a open book exam there that it was based on this dotted line. So sometime you have to make use of this as well. So from exam point of view, you need to have this table and may need to use it as well. Okay, so this is the um, chart which you may expect to use if it asks you to use ideal gas equation with a compressibility chart. And this is table 1 where we want to know what this gas constant R is, and you have to be always careful about the unit what is given, and then do the calculation accordingly. The unit is the most important here in this ideal gas equation, because that's where you tend to make mistake. Okay, like this problem we did in the class is a superheated water at this pressure and temperature, and you need to find the specific volume using the ideal gas equation. I think it should be easy. Ideal PV equals to RT. Temperature is given, but it has to be in Kelvin. Pressure in megapascal, so it should be in Pascal or Newton per meter square. The value of R, so this is for superheated water. So you need to look for the table A1 where the water is here, the R is here, it is in kilojoules, so convert to joule. So we know everything, and then you can calculate this for using the general compressibility chart. So for you need to know how much is G, right? So for calculating G, you should know PR. PR is P by P critical, and this one these are all TR, and TR is T divided by T critical, and T critical and P critical you get from table A1, and then you calculate this value, and wherever it meets, then the value of G would be found through this one. So in this problem you find PR is 0.15 somewhere here, TR is 1.11, so 1 is here, this is 1.11 somewhere here. So yeah, the whole line is the same value, so the intersection of this pretty close to 0.96. We know the G value, and then you are able to calculate the specific volume. Again, sometime like in the open book exam problem, it could relate with the specific volume as well. Okay, so if that is the case, you have to make use of these charts. Okay, so these dotted line here are for the volumes. Okay, so I think so that's it.